Welcome to Radio Systems Design, Module 6, Direct Conversion Transmitters. In this module, we'll be covering direct conversion architectures, as well as some of the non-idealities of these, in particular carrier leakage, amplitude and phase imbalance, and phase and frequency imbalance. So in a previous module, we learned that one of the most common modulation schemes is a simple quadrature modulator, as shown here, where we have an in-phase and an out-of-phase local oscillator that sets two orthogonal signals, the I and the Q, onto an output. So in principle, all we need to do is take the summation of that output and put it through an antenna. And typically to do that, we need to amplify the signal to get any kind of distance for transmission. And what we do is we introduce what's called a power amplifier, And the reason why we call it a power amplifier is that the metric that's used most often is total output power, also efficiency, and then also important in that is its linearity. And unlike small signal amplifiers, power amplifiers tend to trade off linearity and gain in order to get higher power, higher efficiency. So it's not that they're necessarily totally different from a regular amplifier. It's just that their designs are focused on different metrics than other amplifiers. And that leads to architectures in power amplifiers that aren't like small signal amplifiers. In particular, many power amplifiers can be switching amplifiers that have quite a bit of harmonics, but they provide very high output efficiency and output power, and so there's always a trade-off that's there. We'll discuss how to build a power amplifier in one of the last modules in this course. Now practically, typically we're not going to have a single amplifier. We usually have a cascaded stage of several amplifiers. And that's just because, like I said before, typically our goal is for very high output power here at the end, and each amplifier itself may not have sufficient gain, so we just put in some preamplifiers to take care of that. And as I've used sort of throughout this course informally, and I guess we'll introduce it here formally, we call the oscillator that drives these two quadrature signals as the local oscillator. And this just comes from the fact because it is the oscillator that's in the radio, and so if you will, it's the local oscillator that up or down converts the signal. And this architecture, as simple as it is called a direct conversion transmitter, and it is quadrature. Almost all of the digital communication we'll deal with involves a quadrature transmitter. If the input signals here were analog, this would just be a direct conversion analog. So there's nothing really different between analog and a digital from a hardware standpoint for this direct conversion. But we introduced this because we're going to be going into more complicated architectures in just a moment. So some of the non-idealities of the direct conversion architecture have to do with carrier leakage. And we note here that the in-phase and quadrature data at the baseband are directly shifted to the carrier frequency. So as you know, this signal gets up converted right to there. The carriers are generated by the local oscillator, as we mentioned. But in practice, typically this local oscillator should only drive the mixer, but there's going to be a small amount of feed through the two mixers. And if you're wondering how could I possibly leak through the summation devices, this is actually because the local oscillator is generally in a circuit with the other components. So there's either a parasitic coupling or it's going through an actual component such as the mixers. And we end up with it leaking out and it popping right down there on top of our signal. And so this is one of the challenges or downsides of direct architectures, is trying to handle the LO that leaks through. So let's understand a little bit how this affects the signal and the constellation. So what I've written here is simply the signal for the I and the Q signal, and this is our in-phase LO and our out-of-phase LO, our quadrature LO. And remember, I and Q were just chosen arbitrary. All we need is that I and Q are 90 degrees out of phase, so that when they're transmitted, they're orthogonal to one another and can be received independent of one another. So now what happens if a certain amount of carrier leaks to the output? And so what we've done here is we've just added some factor k of our carrier and a small phase difference. So here we have our Q modulated signal, our I modulated signal, and this is just a single tone of the oscillator. And so now I'm just going to break this out of using an identity for cosine of u plus v. If you look at that identity, you'll find it'll give you a product of two cosines and a product of two sines. And so k goes out in front of both. And what you notice is that cosine of phi term here and the sine of phi term here. Typically phi might be fixed, and so this is just going to be a constant. That's not always the case, but you can see here that it's a constant and k is a constant. So what we're going to do is add a little bit of a constant carrier frequency to our final signal. And we then can show that it puts into both of the in-phase signal here and then the quadrature signal here. Both have this non-ideality of the distortion that's been put in. So basically what we're doing is we put a DC offset into the I and Q if our carrier leaks through. And so let's just look at what happens to the constellation. So here's a 4-QAM constellation, and if we have a little bit of carrier leak through, that's going to add an offset to each signal, and it's just going to shift our constellation up in one direction. So that's going to be the effect of a carrier leak through that gives us this DC offset. You might be thinking, well, it's a DC offset, that's not a problem. However, if you imagine that you're a receiver, and what the receiver does is it says anything in this box is 1, 0. And so if your received symbol, if you will, marches out of that box, it's no longer going to receive the correct signal it should. Typically what will happen is we can actually shift these boxes. This is the received box so that it's centered around there. That's something we can do if we want to try to fix an offset that we know that's happened. But if we don't know the offset's there, we'll be looking right around here for the signal, and if it's not there, we could have an incorrect reception or an error. Another thing that happens is amplitude and phase imbalance. So we talk about this local oscillator and these two orthogonal signals. The way they're generated is through quite a few different means. One is a quadrature VCO, where VCO is a voltage controlled oscillator, and it's just called a VCO. A polyphase filter is just a set of filters that basically outputs, if you will, you put in a sinusoid and it's going to output a sinusoid in phase and then a sinusoid that is out of phase. And it does this just by using LCs as a phase shifter to give us these two. Typically, this would be a 45-degree phase shift, and this would be a minus 45-degree phase shift from this original signal here. And they can also be done through frequency division and a number of other means. The reason we describe how this is done is just for you to realize that however we do it, there's going to be some non-ideality that can create two problems. One is that the amplitude of the two signals is not the same, and also the phase isn't exactly 90 degrees. And this actually happens quite often. So let's look at our quadrature signal and see what happens when we have amplitude and phase error in our two local oscillators. So what we're going to do is introduce an unknown amplitude, eta, and a that's epsilon, and an unknown phase, delta, theta. And we're going to break this out just like we did before into the identities. And if you work through the math, you can see we suddenly now have a precursor of the, or prefactor for the sine and cosine. Here, this looks just like a constant, right? But if you look over here, we actually have this signal, and we've got a Q of t. So now our in-phase signal contains the in-phase and a small portion of the quadrature. So any phase imbalance basically takes that orthogonality and breaks it up so that a small amount of either the I or Q gets overlaid into the other channel. And so this distorts the I and Q data. And if you look at a constellation diagram, you can see here that it's been not shifted but distorted. So now one thing you might wonder is what happens if you have a complete 90-degree phase shift. Well, what's going to happen is this is going to move down here. These two are going to collapse, and this is going to move up here. And that makes sense because basically you're either going to have the two signals adding in phase to give you a high signal with a 0-degree phase shift. They're going to add in the opposite phase, so you're going to get superposition again, and then they might cancel one another where you'd have 0. Another non-ideality is phase and frequency instability. We're not going to talk a great deal about this, but you should realize that the oscillators that we use aren't perfect. And so there's two things that aren't perfect about them. The first one is the fact that the frequency is not fixed in time, and it actually drifts over time. And it's not a large drift. It would be maybe a few fractions of a percent. Drifting might happen because you're holding the phone with your hand and you're heating it up, or you're out in the sun, or it's cold. And so temperature is one of the biggest causes of frequency drift. The other one is phase noise. And in the frequency domain, if this is our local oscillator, what phase noise is, it's basically little sidebands because this is moving back and forth just ever slightly, and its change is happening because the phase of the signal is changing randomly, and every time there's a phase change, there's a slight frequency change. Now, this is probably beyond what we're used to thinking about in terms of frequency domain for this course, but what I'm going to do is show you what it looks like in the time domain if we had a clock with phase noise. And so imagine I have a clock running through time, okay? And these edges in time move back and forth. So I've got a certain amount of uncertainty here. And this is called jitter. And I think physically jitter is just a little bit easier to understand. If you have a clock edge that cycle to cycle, it might not land exactly at the period t that you're hoping for. And that variation from where that clock edge lands is jitter, and it's the dual of phase noise for a sinusoid. And this happens just actually from the thermal noise in the oscillators, and it's one of the fundamental limitations of oscillator, and one of the fundamental specifications in looking for an oscillator is what is the phase noise for that. And so let's just take a little bit of a look what happens when this LO is degraded by phase noise. The impact in the final constellation is basically a blurring. And so you'll see that it moves around the constellation. Now, when I say blurring, it's not like a dot that becomes bigger in all directions. That would be just additive white noise. This is still going to follow the trajectory, but it's going to move back and forth along the trajectory. And once again, if we have a receiver trying to find that dot, the receiver box needs to be big enough so that it contains the entire span of what is going to happen. And then finally, typically in a transmitter we need quite a bit of gain, 20 to 30 dB. And that's because we're generating the baseband signals with very low power, and we want to transmit with enough power to reach our final destination. One thing about gain in a transmitter or a receiver that's a little bit different is that because the amplitude of the signals coming in can vary depending on where the system is, we often need an adaptive gain. This is not only to level the signals in a transmitter or receiver, but also could be so that we need to boost power or the amplitude of the signal. So one thing we'll find a lot, particularly in receivers, is an adaptive gain to adjust the signal level. And for the transmitter, we're going to need adaptive gain to adjust for the transmitted power. And just a side note here is it's pretty difficult to provide high frequency amplification. And it's something we have to do, but typically we try to amplify as much as we can at the lower frequencies and then simply upconvert. But we do have to amplify at the RF frequency, if you will, for a lot of architectures also. All right, so this concludes this module on direct conversion transmission. We talked about the direct conversion architecture and 3 non-idealities. The carrier leakage caused the constellation to shift as a whole, but keep its shape. The amplitude and phase imbalance, they caused a distortion in it, so it didn't move from the center, it just distorted around the center. And finally, phase and frequency imbalance caused a blurring of the constellation due to the variations in both the phase and the frequency of the carrier.